Good afternoon, everyone, and welcome to our CAT seminar series. Today, we are very fortunate to have with us a distinguished speaker, and he's a very good friend. And he's quite involved, actually, in pavement engineering and science as well, as he's part of this new Academy of Pavement Science and Engineering. Professor Elie Hajj, who's actually a PhD from University of Nevada, Reno himself, and he's been there studying, doing pavement evaluation and characterization work for many years with his PhD again received there. He's an associate professor, and he's also an associate director of the Western Regional SUPERPACK Center at the University of Nevada, Reno. So his expertise is in the areas of advanced evaluation and characterization of engineered and sustainable pavement materials, mechanistic analyses, and full-scale pavement testing under dynamic loading. On the personal side, I know that he's been working on the stress-based permanent deformation model characterizations and things, and I know he's doing a lot of good work that has the same synergy from our transportation pavement foundation understanding of rutting accumulations, and in a non-destructive way, how to assess that from moving wheel loads and FWD testing also. But today's speech actually is very interesting because he's going to be talking about how to protect pavements, how to actually evaluate pavements under really heavy loads. As you can see, the SUPERPACK, super heavy load movement on flexible pavements is a very interesting topic. And without further ado, I would like to invite him to give us his speech and hear from him this exactly interesting speech. So.
Thank you very much for the introduction, Professor Tutumur. I would like to start by saying thank you for the opportunity to be here. It's my pleasure, and I'm honored to be here. And I'm looking forward. I didn't have a chance to meet all of the students in person. I'm looking forward after this talk really to have a more one-to-one conversation with the students and more interactions. So my talk today is going to be basically on federal highway projects that we are in the process of wrapping up. Actually, the reports are now being under review, and then we're going through the editorial review and so on. But as Errol mentioned, it is related to developing analysis procedures for the evaluations of super heavy load movement on flexible pavements. So I've seen a lot of rigid pavements around here, but I've also seen flexible on top of rigid pavements. That's not basically what the scope of this work. This scope was basically only based on the flexible pavements. But I'd like first to acknowledge, of course, the support and the funding from the Federal Highway Administration throughout the past years, and of course the support of FAA, Caltrans, and the LANAME UCR in Costa Rica for their also support in providing data, a lot of useful data from them, heavy vehicle simulations, and so on. What the team for this project basically, and some of you might be familiar with those faculties, but I was leading the project as a PI. We also had Professor Siddharthan from UNR. If you're familiar with the 3D Move analysis software, he's the one that developed originally the theory. He's behind it. When I first used it, it was 2001, around 2001, right? 18 years ago, it was, of course, a DOS version. And then if you're not familiar with that, you know how to get data out of the DOS, how to know if the software is done or not. You see those dots blinking, right? Waiting for the run to be complete and all of that. But we took that software and we improved it under another FHWA contract. We made out of it, the 3D Move Windows-based version. And I'm going to show you also today some of the improvements to that software that went into the package that we call SUPERPACK. And also Sharif Al-Fas, his expertise is in large-scale testing. He managed the NIST Center for Bridge Engineering and so on because we were doing full-scale testing on this experiment. So he was also a part of our research team. And of course, our research scientist, Murugai Peratipan. And we had several graduate assistants, that worked on that project throughout the years. They had a different expertise and they have a different scope, throughout. I really would like to acknowledge them all one by one because they contributed a lot for the success and the work for this project. With no further ado, I'll start with an overall objectives, and then first by defining what's a super heavy load. You know, under the overweight, we have different categories. But when we talk about super heavy load, typically they are defined by the gross vehicle weight. And in general, we're talking about more than 250,000 pounds, the gross vehicle weight. Now, we've seen as part of our reviews, you know, some of those vehicles, they can go up to 5, 6, or even close to 7 million pounds. So imagine how heavy those vehicles are. Now, typically, to distribute that load over the pavement, what they end up doing are changing the axle configurations and then changing the number of tires per axle. So you're dealing with a more or less non-standard configuration. So if you're all familiar with the 13 different FHWA vehicle classes, right? None of these will fit under one of those categories. Okay? So we cannot use our traditional design and analysis approaches to solve or to basically assess whether we can have that move, yes or no. Okay? This is part of the synthesis that was completed in 2015, and this is kind of the number of permits received. And almost 36% of the state highway agencies receives more than 1,000 permits per year for super heavy load vehicles. I don't know if you can see it may not be very clear in here, but I was trying to highlighting a little bit the configurations of those super heavy load vehicles so it get you a little bit of flavor of, what are we dealing with. Maybe if we dim the lights a little bit, we might be able to see it better. So as part of this, we went and then we reached out to a few states, and then we asked them for actual permits. Part of that, the objective of that was to find out, okay, what kind of configurations they've been getting as part of their permits, what kind of axle loads, what kind of tire loads, right? And I'm summarizing here for you just 3 cases from Arizona DOT, Louisiana, and New York. And if you look over here, basically, you have information related to gross vehicle weights. You look across, right, you see in some of the cases, for example, in Louisiana, we got permit in about almost 3.6 millions, right? Now, that doesn't mean this is all what they get. They may get higher. Again, we took a sample, right? And then just to get ourselves familiar with the type of the configurations. But what's interesting is the number of tires per axles, right? It varies from one permit to another. The spacing between the axles and the number of axles, it varies from one permit to another. But also, you look at the tire load range, they could be as close as what you might observe in a typical steering axle, 18-wheel truck. You get what, 12,000 pounds, right? The legal load limits, you get 6,000 per tire. You can see that on a super heavy load, but you can also see some of them as high as 16,000 pounds per tire, right? And we all know, if we go back, right, to the AASHTO 1993 and we look at the equivalent axle load factors, and we see that growth, it's exponential, right? So imagine that what kind of damage that kind of super heavy load vehicle might be causing to your pavements, okay? Here are some examples of those configurations. This is an actual permit, one of the permits. This is the one basically that has a 3.6 millions. All right, how many axles do we have? 28 axles. How many tires do we have? 224 tires. What's the load per tire? 16,000 pounds. Now you go take your Pavement ME design and try to design for this, right? So apparently we're not dealing with the traditional type of configurations. All right, so we need to do something different. And the idea over here, remember those permits, though an agency can have what we call a single permit or a multi-year permit. Those are typically as a single permit. One pass, actually in a single permit they tell them you have this week, right? And you can do your pass within that week, or even they tell them you can do it only between 5 p.m. and 5 a.m. in the morning. So they even specify the time of the move. All right, so they're very specific. Very well, how are we going to then assess whether we can make that move or not? Given all those variabilities, given that the route. What is the route? What's the characteristics of the pavements, right? Especially the subgrade material properties and so on. How are we going to do that? Well, you can come back and say, I have a finite element model. I can model moving trucks. I'm going to take it and model it, right? Fine. How many axles do you have? 28, 224 tires. Tell me when you're done, and then we can check the results, all right? So it's going to take time. So we need something that can be implemented by the state highway agencies. So what we came up with, and we're going to talk about, is how we can take that 224 tires and narrow it down into a number of tires that we can handle in our traditional, pavement analysis software. So if I'm going to step out and now think about, now that you know what's a super heavy load, what are the critical concerns with any super heavy load move, right? So they're listed over here. And I'm going to go one by one. First, which we talked about, is the non-conventional configurations, not only in terms of the axle, tires, and the axle loads and the tire loads, right? The second one, remember those typically are moving at a slow speed. And for flexible pavements, being a viscoelastic material, slow-moving vehicles, basically heavy vehicles, will have a tendency to cause more damage to your pavements. So the viscoelastic property of the asphalt layer has to come into play in your analysis. Second, we looked at 16,000 pounds, right, over a wider area. Now, what happens is, as you go deeper into your pavements, those stresses are going to start overlapping, right? So there's an impact of that increase in the state of the stresses on your unbound material, and specifically your subgrade, which is typically the subgrade is our weakest layer in our pavement structures. So somehow accounting for the state of stresses of an unbound material needs to come into play, into your analysis, because we're not dealing on a typical 18-wheel truck. I have a typical resilient modulus or property for that subgrade. Now I'm dealing for the different configurations. Then my subgrade properties most likely is going to be different, right? Because it's stress-dependent material. Then you get into the first check that we would want to do is the likelihood of instantaneous shear failure, right? We're going back to the basics, bearing capacity type of failures, right? Can I say that this is more like a footing, right? A long footing, right? Which I may end up with some bearing capacity instantaneous failure, which happened in some of the permit. It may not be frequent, but it happened, where the minute they get the pass, they get failures, bearing capacity failures. So that needs to be somehow checked as part of the analysis procedure. But at the same time, yes, we haven't reached bearing ultimate failures, but hey, my deflections are excessive. From a pavement engineering perspective, I cannot live with 2-inch deflections, right? We're talking about 20 mils, 30 mils, right, as a service limit, or 50 mils. So we need to check for excessive service deflections, because that may be controlling my criteria. But in a lot of cases, also those moves happen in rural areas, where either you don't have a shoulder, or you may have a sloped shoulders. And then slope stability might become also a problem, okay? You're going to need to check into that. And another very important aspect is buried utilities, which is, in a lot of cases that we looked at it kind of the concern number one, right? Because if your pavement fail, all right, maybe we can fix it. But if you have a gas line or a pipeline, water pipelines, and they break or they crack, it becomes a hassle. It becomes a big problem. So we also need to check for any buried utility failure, right? Now, assuming you pass all of these, at the end of the day, what you'll be interested in, I want to know now, what's the pavement damage associated cost? Because this super heavy load vehicle might still be causing some damage to the pavements, and I need to basically have a reliable or representative permit fee that I can charge. We've looked at some of the permit fees without naming any states. There are states where they use just a flat fee of $25 for any super heavy load or overweight vehicle pass. And it's more like an administrative cost, really. Okay? Very well. So you look at that. That's a super heavy load. It is in somewhere in the middle of nowhere, right? Most likely the pavement is not thick enough, right? But yet we still have the pass going. If you notice, there may be a little bit of shoulder here on the side, a sloped shoulder, and there's not much room for a shoulder, really. So that super heavy load might be driving too close to the side of the road, and then you have a shoulder, right? So you may end up with a sloped shoulder bearing capacity failure. You may end up with a bearing capacity failure in your subgrade. You may be causing excessive deflections in your basically truck and so on. So that's in the summary what we're trying to do when we say analysis procedures, right? Because there are several analyses that we have to go through to be able to accomplish that. And this is a flow chart, and I know the font is too small, but I'm gonna put on the sides all those different steps. But this is kind of the overall chart that you need to go through every time you have a permit and you want to assess a super heavy load move. The first one is your SHL vehicle analysis. And what I mean by that is you definitely have to define the configurations and so on. But also, we came up with an approach, like I said, that we take the entire super heavy load vehicle and we narrow it down to what we call a nucleus. And we do the analysis under the nucleus. All right? The second one is defining of course, your pavement layer properties, but most importantly, the material properties. Right? There's a pavement layer thicknesses and so on, but the representative material properties under a super heavy load move for your asphalt layer and for your unbound materials, right? And right away, when we talk unbound materials, it comes to your mind, okay, what is the state of stresses under super heavy load? And let's use that state of stresses to come up with a representative modulus for the base and the subgrade. Okay? Very well. Then you start getting into your analysis. The first analysis, which is the global failure, if you want to call it, or we call it the ultimate failure analysis, where you do a subgrade bearing failure analysis. And if you have a shoulder, you go through your sloped shoulder failure analysis. All right? Now, to do a bearing capacity analysis, if you remember your, what's the course number here? Where you talk about the shear strength parameters and or foundation. All right. So geotechnical courses, you need the shear strength parameters, right? Which means the cohesion and the angle of internal friction of your subgrade. And we all know the best way to do that is go out to the field, get a sample, bring it back to your lab, test it in the lab, and develop your failure criteria and your CNF, right? However, remember, we're dealing with a permit office. And they don't have the time to do that, and they don't have to do it, for every permit and so on. We wanted to rely on some kind of a non-destructive approach. This is where we use the falling weight deflectometers, which is typically used to back calculate the moduli of the different layers. We use the same approach to extrapolate that theory and back calculate the C and phi of your subgrade. And I'll talk about that a little bit over here as well. Okay? That will allow you to carry over with those two analyses. Then you have to do your buried utility risk analysis. And there are some good criteria based on the, whether you have a flexible or a rigid plate. Flexible or a rigid utility, right? You need to check for those. If not, of course, at any time, if you fail any of these, we have to do some mitigation, right? What would be mitigation? You can put a steel plate on the top. You can put a wood pieces. You can have an aggregate base, right? I've seen cases where they put a 10-inch of aggregate base because they had a concern with the buried utilities, right? But of course, that wasn't a long hole. It was a very limited section, but they've done it, okay? So those are mitigation techniques where you reduce the level of stresses into your utilities and subgrade and so on. And then after you pass all those checks, basically, yeah, this is all good. I'm not going to have this instantaneous failure. I'm not going to lose my job, but I may be causing a lot of damage, right? Because I'm causing excessive surface deflections. That's why we do a check for localized shear failure analysis and the deflection-based service limit analysis. And we use here one of the findings from Professor Tuttemuller to come up with the limiting criteria. And we'll show that also in a bit in this presentation. And then finally, if you pass all of that, then I can consider that pass as a number of repetitions, right? from the beginning, I cannot come up with the cost associated by saying, oh, I have 24 axles, let's see how many repetitions, and I follow our minor rules, damage calculations, and I get a cost. This is only will be applicable when you pass all those criteria and you narrow down your problem into something similar as a number of passes after you pass all those different criteria. Very well. Then this is all good. We developed the procedure, but at the end of the day, for implementation purposes, you need a tool, right? For state highway agencies to be able to use, this is where we came up with the SUPERPACK, stands for Super Heavy Load Pavement Analysis Package, right? And you know our logo is the pack, right? Wolf pack, right? We made it to the Sweet 16 this time, but we lost, but at the end, but we made it, right? After 14 years, right? Right. You were cheering for? Okay, good. Very good. So it took me some time to come up with that name, but it clicked. In the middle of the night, it just came. SUPERPACK, right? So this is basically what the basis for the tool. This is just the GUI of the main one. So right now, it's a MATLAB code. We're doing alpha testing internally and all of that, but eventually it will be part of the deliverables for the FHWA, and then to follow up with some case studies. It does, if you, like I said before, we have the 3D move analysis software, right? So the engine or the pavement model behind the SUPERPACK is 3D move, all right? But we call it 3D move enhanced because we made some enhancements. And I'm going to talk a little bit about those. What does 3D move can handle? It basically can handle moving loads at a constant speed. It can handle any shape of the tire configurations, not only vertical, but also you can introduce your interface shear stresses into the softwares. It can handle the viscoelastic material property of the asphalt layer. But when it comes to the unbound material, it goes with linear elastic properties. Okay? That's why, and as I said, it was developed at UNR, so we had that advantage to make use of it in the SUPERPACK. Very well. So the 3D move basically used the fast Fourier transformation. So to solve, basically what we're solving for is the displacement, okay, in a frequency domain. If you're running a static analysis, this is how you describe your load at the surface. X and Y are basically your dimensions. X typically for us is the travel direction. Y is the transverse directions, right? And then if you have a moving speed, and in the case of the 3D move is a constant speed, then we introduce another variable, which is C. So we substitute from X minus CT. C is basically the speed of the load moving. Okay? So that will allow you to characterize a moving load. So by looking at this, it is basically, it's telling you that you're gonna, it solves the problem as an accumulation of multiple frequencies. Any shape at the surface, basically you can describe it by a summation of waves, right? With different frequencies and different amplitude. When you sum them all up together, they will give you that shape that you are looking for. And that's why it can handle non-uniform contact pressures, whether in the vertical, horizontal, or transverse directions. So the enhancement that we introduced, that's why we're calling it 3D Move Enhanced, we actually recoded the 3D Move in MATLAB, and then we made adjustments. What are those? We use the inverse Fourier transform technique instead of, so currently the 3D Move, I don't know if you have used it before, but you have to specify, right, the location where you want the responses, and you can get the response as a function of time. Okay? What we did as an enhancement is now we get a surface plot for the entire domain. Okay? And that was important for us because if we want to go through into bearing capacity analysis, we want to calculate the average, pressure on top of the subgrade and compare it to the ultimate, right? So we want to, it's nice to have the surface plot so we can do that analysis. Very well, but that might be costly. Why? Because the runtime might be longer. So that's why we introduced a parallel processing. And then we cut down the time significantly, okay, on the runs. And also at the same time, we introduced different bonding conditions. And that was important specifically because if you want to go through mitigation and you put a steel plate on the top, there's no bond between the steel plate and your existing asphalt layer, right? So you want to be able to model that. To do so, we use the basic formulation, right? And we use the inverse Fourier transform to do all of that. But we take it also one niche higher, which is not part, and I put that note over here, not part of SUPERPACK, right? This is a contribution of the Farzan, the PhD student, as part of his project. We are in the process of developing something called now 3D Fast, right? So what is 3D Fast? It stands for 3D Fourier Analysis of Pavement Structure and then Transient Loadings. In the 3D Fast, and again, I emphasize, not part of SUPERPACK, but in the 3D Fast, what we introduce another variable, a Fourier variable, which is time, which was very important for us. Why? Any idea why? What will allow us to do? We can change the speed. We can model now variable speed. Or I can model an FWD pulse. Or I'm going to show you another application where I can model actually the impact of pavement roughness, where you have dynamic loading. As you're moving, the loads vary. So I can vary the load as a function of time. Okay? That's what basically the 3D Fast will allow us to do. So the main difference between 3D Move Enhanced or 3D Move and 3D Fast is when you're solving for the waves, right? We are moving those waves across my domain. That's in the 3D Move Enhanced. But in the case of 3D Fast, because we introduced time, now we have time as a variable. You can see even the amplitudes will change even as a function of time. Very well. What is the application? Here's one of the verifications, simple verification. We took a Kelvin model where you have the theoretical solution, and then we simulate that model, right? We use an asphalt layer with the Kelvin properties, and we simulate it in the 3D Fast. And then your theoretical solution will perfectly match with your, eventually, your 3D Fast calculations. So that was just a simple basic, just to make sure that the model is functioning properly, right? Very well. What kind of applications? I'm going to show you here. This is from the 3D Fast runs. It's basically we're taking, in this case, we just took a circular load, right? But again, remember, you can model any shapes. But while that load is moving, we're changing the amplitude of the load, right? So remember when we do design, we design for static loads. But in reality, right, you have the roughness of the pavements coupled with the dynamics of the trucks, the suspensions, the tire types, and so on. Then you have dynamic loads, right? So if you know what are those dynamic loads, you can model them over here. On the right-hand side is when we model the pavement as viscoelastic, the asphalt. On the right-hand side is when we model it as linear elastic. Should be a video here. So now you see the load moving on the top. The bottom is the response to surface deflections, right? And as the load is moving, you see how the surface deflection basically is changing, right? And we put an arbitrary function just to show how it's moving. But now once the load passes over, because it's a viscoelastic, little by little your surface deflection is going to basically, eventually if we left it longer, it should goes back to 0, right? But we stop the time. On the elastic side, it should be the opposite. It should be instantaneous, right? The minute the the minute the load is over, everything should go back to the initial condition, right? And that's what you see here. The same load, you end up with the different responses eventually. But then as the load disappear, right, we still have to define a domain. As the load disappears, everything goes back, and then boom, to 0. Okay? So that aspect is what we call, modeling the impact of pavement roughness, right? Like what you do with a quarter car simulation. You input a profile. What do you get out of the profile? You get the displacement, right? But you can also get your dynamic loadings if you want to. And if you have your dynamic loadings, you can study the impact of pavement roughness, right, on your pavement responses and eventually your pavement damage. Very well. Let's go back now to SUPERPACK. Okay? As part of the main menu, there are 4 main sections. The top section is where you define your pavement structure. You define the layer thicknesses, the type of the material property, whether you want to use viscoelastic, linear elastic, but we added something called stress dependent. So what we mean by stress dependent is it's more like the iterative process, right? It's not a true finite element type of analysis. Here we're using finite layer approach, which means every layer would require to have one property, okay? You also specify the speed of the move. You specify the analysis temperatures, whether you want to have a mitigation or not, and what kind of mitigations. If you have a buried utilities, you have to specify that up front, and whether it's flexible or rigid. Then you have a non-destructive testing. So one of the major input for SUPERPACK is really non-destructive testing. And why? Because we use the FWD data to first back calculate the CNFE for the subgrade, to back calculate the moduli of the various layers at different load levels, and be able to develop the stress-dependent model of the subgrade material. So we need the FWD testing or at multiple load levels, okay? And you go into some pre-analysis. The pre-analysis is where basically we start defining that we have that large area for the truck. We're going to start defining is what is a nucleus that we're going to do the analysis for, right? Because we cannot model 224 tires. We're going to model what we call a nucleus. We do the material property, representative material property under the super heavy load and under the truck. We select the material property internally. We come up with the subgrade shear strength parameters. So this is where you collect all your pre-analysis data before you go really to the analysis, where you have a bearing capacity analysis, slope stability analysis, service limit analysis, buried utility, and cost allocation. Okay? Once you do all your pre-analysis, you collect your data and everything, then you can move on and start with your analysis. You don't have to go to doing all your analysis, right? Because some might not apply to you or might not be of interest to you, right? So you can just pick which one is applicable. Very well. Now, part of the whole approach, because we were developing new methods, right? We needed to verify them. Not only numerically, which we did, but also they need to be verified with some actual measurement. So we made use of our what we call PAVEBOX, which is 11 foot by 11 foot by 7 foot height, to do 5 different experiments for full pavement structures, where you have, for example, 5-inch asphalt on top of 10-inch aggregate on top of a subgrade. Okay? We did experiments where we have full pavement structures. We did others, I don't know if you can see it, but it has a shoulder, right? And then also some others where we constructed buried utilities. This is a flexible pipe, steel pipe. This is a rigid buried utility, which is a box culvert. Okay? Now, why are we doing these two? Well, remember, as I said, 3D move is a finite layer, right? So if you have discontinuity in your layer, it's not going to estimate your stresses or responses or whatever you're looking for properly. So there will be some kind of an adjustment factor for the stresses. So every time I have a shoulder, I cannot model it with 3D move. But we developed stress adjustment factors that I can use in my bearing capacity analysis. Every time I have a buried utility, I want to calculate the stress level on top of the buried utility that goes into the analysis approach, right? I might also need a stress adjustment factors, right? That's what the experiments helped us to do, is to develop those factors by instrumenting those pavements with, of course, pressure cells, strain gauges, and so on, and then compare for full pavement structures versus a pavement structure with buried utility, or a pavement structure with a sloped pavement, and so on. Very well. So starting with the super heavy load vehicle analysis, the first step to get into what we call a nucleus is we're going to divide that super heavy load into groups. We call it axle groups. Here are 3 different examples out of the permits. Your super heavy load might be continuous axles, might be different dollies, right, with a given spacing, or something similar to a more or less traditional truck. Okay? All of these were more than 250,000 pounds. Okay? So what we define first, an axle group, based on the spacing of the axles. Every time the spacing between the axles is less than 60 inches, will be one group. When we exceed 60 inches, then it will be considered as a separate group. Okay? Now, within each group, we may still end up, look at this, you still end up with 224 tires, right? Or even here, that's a lot. Then we go through a process to determine what we call a nucleus. What is a nucleus? You start with one tire. You calculate the responses at the point of interest, let's say on top of the subgrade. Then you add another tire. You see the impact of that tire in one direction. You keep on adding until that impact becomes less than, say, 5% or 1%. Then you can say, you know what, that tire now it's further away. It's not influencing the responses under my point of interest. Then you do it in the other directions. And then you can end up with what we call a nucleus of an axle group. So you may have 10 by 20, but your nucleus is only 5 by 5 or 5 by 4. It all dependent on the axle load, the tire load, the axle spacing, the configuration, and your pavement structure, how deep it is, right? Whether you're having interactions or not. Then, for the nucleus, we carry over the analysis. Okay? So we simplify the problem into something more realistic. We call it the nucleus. So for example, for this super heavy load vehicle, this has turned out to be your nucleus. Instead of 224 tires, it is really 5 by 5, and you calculate the responses, the critical one under the center one. Yes?
How does that relate to the asphalt? That assumption, how does that deal with the asphalt?
In terms of what?
Viscoelastic response.
The viscoelastic response of the asphalt, you're still handling it because they're not load related. They're more related to the speed, right? Speed and temperature. So you're still dealing with the asphalt as a viscoelastic material properties. But then when you do the analysis, you do the analysis with this configurations, right? Now, also, when you do the analysis with this configuration, if you go at the middle of the nucleus and you calculate the state of stresses of your in the unbound materials, then you will use a representative modulus for that unbound materials. Okay? This is just from a GUI. It's done basically. The MATLAB code will take the axle, group them, and then it goes through the process to come up with a nucleus. So it's been coded automatically so that the user, state highway agencies, they don't have to worry about it. It is done internally. Very well. The next one is you need your pavement material properties. So for the asphalt materials, we're going to use basically the dynamic modulus of the asphalt material, which means, again, remember, you're doing the move. This is not, most likely, it's not a new pavement, right? It's an existing roadways. So you need the dynamic modulus of the existing asphalt layer. Now, you can go out, take cores, do small diameter specimens, get your E star. Very good. Or you can follow the ash-to-wear pavement ME process where you do FWD testing and then you back calculate the damage dynamic modulus. All right, so any way you can get the material properties, whether from cores or from non-destructive testing, to develop your dynamic modulus of the asphalt layer. For the unbound materials, like I said, it's an iterative approach. You need the stress-dependent behavior. That's why we will require the FWD testing at the multiple load levels, so that will allow you to develop the resilient modulus relationship as a function of the state of stresses. And then you look at it, what is the state of stresses under the nucleus, and then you assign the appropriate resilient modulus. And then the subgrade shear strength parameters, we develop a novel approach to back calculate the CNFE from the falling weight deflectometers. So you get your FWD testing at the multiple load levels. And we're recommending, if you're familiar with the falling weight deflectometer, typically those can go up to 27,000 pounds. All right? Now, if you have a heavyweight deflectometer, that can go up to 54, or some might go higher even. So you have to do it at the multiple load levels. You collect your data. What do we do with that data? With the data, we do the back calculations, and we can end up with the back calculated moduli for every load level. So if there is any stress dependency in the system, right, especially in the unbound material, right, we're not talking about the asphalt layer, we will basically capture that with the FWD testing. And then we take those back calculate moduli, and we resimulate, if you want, the FWD load levels with a 3D move, but using a linear elastic. But at every load level, we use the appropriate back calculated moduli. And we look at into the subgrade, and we calculate the stress tensor into the subgrade. In other words, the state of stresses within the subgrade. So you're going to end up with a state of stresses. Let's say, for example, here I have 1, 2, 3, 4, 5 FW load levels. I'm going to run it 5 times with the back calculate moduli for every FW load level. I'm going to end up with 5 different state of stresses in my subgrade. Then we're going to use the concept of invariance to convert that state of stresses in the pavement to a state of stresses in your triaxial setup, where basically you have confining all around and you only have a deviator stress. So we match the invariance between pavement and lab. So we converted the problem from a pavement problem to a lab triaxial problem. Now, if you've run a triaxial test, you can assume, especially for softening materials, that if you are running a triaxial test and you plot the deviator stress versus your axial strain, you can assume or you can fit a hyperbolic relationship. And typically your sigma df, that means your deviator stress at failure, is that asymptote at the top, right? Now in the lab, you test at all those different levels and you kind of almost measure sigma df, right? What is sigma df? In the pavements, right, we're doing FWD testing. So most likely we're testing in this range. So we're extrapolating, if you want, the hyperbolic relationship. So I test at the lower state of stresses. I assume a hyperbolic relationship. If I rearrange that hyperbolic relationship in a different form, if I plot it in terms of strain over sigma d versus strain, the slope, the inverse of the slope of that line is really my sigma df. These data points are coming from that FWD process, right? FWD, back calculation, 3D move analysis, state of stresses, match the invariant will give me those points, right? And then if I fit a line, straight line, then I can get the inverse of the slope. That will give me sigma df. We verified that with actual lab testing of different type of material. And then we verify it also with FWD testing and with numerical simulations. It works. It works for soil softening materials, but you need to be above a certain sigma d level. And we're saying that when you do your FWD testing, you have to be at least, so your highest load level should be generating a sigma d greater than 30%, about 30% or more than your sigma df, right? So you won't be too much on this side, right? Otherwise, you'll be extrapolating too much. Then the error becomes large. You're using small stress level to extrapolate. What did we, basically how we use it, the best way we find out to use it is we use a more Coulomb failure envelopes, and then we have the stresses now, and what we do basically, we assume a phi value based on the soil classification, a range of the phi value that will allow us to back calculate a range of the C values. So at the end of the day, you end up with a phi average, if you want, plus or minus standard deviation, and a C plus or minus standard deviations. And you can select whatever you feel comfortable within that range. How did we verify it? Like I said, we did numerical simulation using Elie. Have you heard of Elie? Maybe. That's another talk. Will come another talk. All right? And then that's where we did the forward and the backward. Because Elie, the beauty of it, though it used linear elastic for the asphalt, but use stress-dependent material property for the base and the subgrade. So we did the forward calculation, came up with a deflection basin, and then applied the same concept to see if we can back calculate the C and the phi that were used as an input into the software. But also we used our large-scale pave box experiment to verify the concept. And once we were comfortable with it, we went and we used HVS data. We used the FAA Roundup study extensively, and then we used the LANAM, also Costa Rica HVS data, where they had measured CNFE for the soil, but they also had FWD data at multiple load levels that allow us to prove that. And the correlation is pretty neat. This is showing both, either C or phi versus the actual, the measured versus the estimated. I mean, this is very good in terms of, I mean, I don't know if should I say that or not. But when I worked at Terracon Consulting Engineers, I had to set up the lab for direct shear testing and all of that to measure the C and the phi and spend the time, get it accredited, and make sure everything is working fine. And then once I get the C and the phi and I take this to geotechnical engineers, very good. Now we're going to go assume C equal to 0. Here's phi. So it's good. I think giving the way based on the circumstances and how we use that, this is very good. We're very happy with the results. And then that will allow you now to carry on and do the abating capacity analysis. This is also the tool under the SUPERPACK, where it takes your multiple FWE load levels, and then it basically fit in the model to come up with the K1, K2, and K3 for the nonlinearity. Now, if there's no, like for example, a lot of the cases we find out that you may not end up with nonlinearity in the base material, so then this will, eventually will be depending if, in the case of the base, this will be 0, then you'll end up only with K2. Okay? Very well. And this is basically the modules where you can get the C and the phi. So like I said, for a range of phi value, you get a range of C values. And we report here the average, but you can always overwrite and decide what kind of value you want to go with within that range. Now that you have your C and phi, you can carry on with your bearing capacity analysis and your slope shoulder failure analysis. In the case of the bearing capacity analysis, so you have your super heavy load. We're going to basically calculate what is the state of stresses on top of the subgrade. And because in order to be able to use the Meyerhof equation for bearing capacities, you need to assume a uniform stress level. And that's what we do. And then we calculate the applied stress, if you want, average stress, coming from a super heavy load to your ultimate stress. Okay? Your ultimate stress is from your shape function, the Meyerhof equations. Your average stress is by integrating the vertical stress over the nucleus area. All right? And then for the slope stability of the shoulder, we use the basically the wedge failure. And then same thing, you define your shoulder, and then we gave the flexibility in the software that you may have a different pavement structure in the shoulder than your main roadways. So you can define that, right? And then we're looking into the factor of safety against slope stability failure. Like I mentioned, because in the case of the 3D move enhanced, we have a continuum, we have a finite layer, we need stress adjustment factors. And this is where we use these two experiments, full-scale pavements versus the slope pavements, with all different kind of instrumentations to verify how much your state of stresses are going to increase when you are closer to the shoulder and you have a shoulder, and come up with an adjustment factor. In this case, we ended up with 1.6. The range was anywhere between 1.4 to 1.8, but the majority of the measurements were about 1.6. So in other words, if you're using 3D move to calculate your vertical stress, you have to multiply that by a factor of 1.6 to simulate the effect of the shoulder. Okay? You pass that, you have a buried utilities, then there are some very good publications, right, between the American Lifeline Alliance guidelines, the Canadian Energy Pipelines, the ASH to LRFD for rigid culverts. There's an NCHRP studies. There's a very good publications, but not all of them covered all the aspects. So we tried to merge them, if you want, into one. So we really didn't develop anything new other than we took all of these and then we said, here's the practices from all those different guidelines, and we put them into one flow chart, if you want, for flexible and rigid. And then we verified same thing in our experiments, actually. We built a culvert over here, and we had a steel pipe all instrumented, right, even from the inside and the outside to measure what kind of stress level we're getting on top of the utility and at the bottom of the utility. But also we had LVDTs internally to see the deflections. Right? And this is where, for example, when it comes to the fixtures, this is where we use a 3D printing to get all those fixtures, right, to make them fit properly with your utilities. We go now into service limit. You don't have any failure. You're not going to get instantaneous failures, right? You have a little bit more at ease, comfortable, but still yet you may generate significant state of stresses. And we did localized shear failure analysis, where basically we looked at the Drucker-Prager failure criterion. Now that we have the CNFE, we can calculate a factor of safety and find out where the factor of safety is minimum. So you see now, this is, for example, on top of the subgrade. And then that's actually the factor of safety. But to calculate the factor of safety, we generated on top of the subgrade as a function of, under the nucleus, we generated the surface plot for the stresses, which allow us to calculate the factor of safety. And in this case, basically, you can look where's your factor of safety is minimum and not, and so on. A lot of the time, what we find out that on the edge of the super heavy load vehicles, where you may have the lowest factor of safety, which kind of makes sense, right? If you're looking into some kind of a shear failures, it would make sense. If you go in the middle of the nucleus, actually you have more confinement, right? So your factor of safety will be larger. Now, when it comes to the deflection base, which is very critical, and actually we're finding out more and more this is going to be the most controlling once you pass, the major instantaneous shear failures, we want to make sure that we didn't end up with excessive failures, right? We wanted to tie it back to the falling weight deflectometers testing. So the way we did it, based on the FWD, you have your surface deflection, D naught, right underneath the plate, versus your FWD load, right? That's the relationship that you see over here. But from your analysis of the nucleus, you have the maximum induced surface deflection, right? That's your D0 max under the super heavy load nucleus. So that will give you an equivalent FWD load, an equivalent, right? So in other words, I have to load my FWD load plate to 25,000 pounds almost to get the same D naught as the one I'm going to observe under a super heavy load vehicle move. This is very good, but I need to compare it to a criteria, right? Where did we come up with the criteria? Luckily enough, Professor Tuttemuller worked on that. So what we went by with the shear stress ratio, the range that he developed between 0.7 and 0.9, right, in order to avoid excessive rutting problems in your subgrades. So what we did is now we calculated the shear stress ratio underneath the same FWD load levels. So this is coming from the 3D move calculations, right? Tau applied divided by the maximum tau. So you see how much that C and F helped us to do a lot of things once we back calculated those. And then now we look, okay, if I'm targeting 0.9, okay, what is now the equivalent FWD load? The equivalent FWD load is 16,000 pounds. So in other words, this is telling me for that given structure, if you don't want to, generate excessive stresses in your subgrade, you shouldn't be having a load larger than 16,000 pounds. In this case, if you're comparing this to this, it's significantly larger. This is where mitigation would be needed, right? Would be warranted. You have to do something to reduce that state of stresses in the subgrade. This is basically out of the SUPERPACK, where it now again it gives me the factor of safety for the localized shear failures, and also that process that I just described over here. We gave the option to the user to select the value between 0.7, 0.8, and 0.9 for the shear stress ratio. Okay, they can select what level they want. For example, at 0.7 is 10,000. This is 24,000. Of course, in this case, you shouldn't allow the move, or if you allow it, you should do mitigations.
You can lower that ratio too.
If you want. Right now, we got it fixed between 0.7 and 0.9, but it's just a drop down. So we put we put 0.7, 0.8, 0.9, but you can adjust it. All right, you passed that. Now you go to your, I say, good. I got it all done. I'm comfortable. Now I need to charge them, right? How much should I charge? Now we take the concept of number of repetitions and the minor rules, right, to calculate the damage. But the way we're going to do it is we're going to say you have the nucleus and you have the repetitions of the nucleus. So if you're familiar with the Pavement ME, right, we divide it into single axle, tandem axle, tridem axle, quad, and then we say we have X number of repetitions for the single, Y number of repetitions for the tandem, and so on. Here we're going to say you have X number of repetitions of your nucleus. All right? And then we do it under your standard truck. We call it reference vehicle, which you have to define in the software. So if your reference vehicle could be an 18 loaded wheel truck to the legal load limits. right? And you look at it and you see what is the damage. And this is the damage, in this case, for example, the AC permanent deformation. Right now, we're considering 3 types of distresses: AC permanent deformation, AC bottom-up fatigue, and the subgrade rotting, okay? Or even the unbound could be the base, okay? These are kind of the distresses that we are considering for the pavement damage cost allocations. And we use the same approach developed by Tirado in 2010, but we added a flavor into it where we introduced the remaining service life. And the concept came from the fact, well, this super heavy load is going to move on top of a pavement that's been already 20 years in service. It's already beaten up. It doesn't sound fair to charge them as if it is just a brand new pavement, right? And you can say maybe because it's already rough, they're going to spend more on the fuel and all of that, right? So we need to give them a break. So that's why we have a remaining service life factor. We call it the RSL. And then the software basically, once you provide the necessary information, it will do the calculation for you per trip, per lane mile, and then per trip, basically, because every trip might have a different miles. Here are, what I'm going to go through is basically a couple examples, right? Just to give you a flavor of what kind of output you might get out of the softwares. Here's the 2 actual cases for permits. Both are coming actually, the reason you're seeing LA, because these are Louisiana permits. It has the dolly case, right, versus the continuous case. And the 8 number over here, because it has 8 tires per axle, and the 12, because here you have 12 basically tires per axle. And then the load, tire load, is significantly different between the two, 6,000 versus 16,000. The gross vehicle weight here is 3.6 millions. Here is about 1.7 million pounds. Okay? Now, if you look at the spacings and all of that, they're comparable in this case, except, of course, between the dolly, the spacing is larger. Very good. So we had a pavement structure. We had the FWD testing at 3 different load levels. We did use the FWD data. We went through the back calculations. In this case, the pavement structure was 5 inch of asphalt, 9.5 inch of crushed aggregate base, 12 inch of sub base on top of the subgrade. The back calculation really didn't show any stress dependency for the base. Okay? So we ended up with a linear elastic property. We saw a little bit of softening behavior in the sub base, but also in the subgrade as well. We used those information, like I said before, to remodel the FWD testing, and then use the equivalent state of stresses, right? And then assume a hyperbolic relationship for the subgrade, and then come up with the C and a phi. And then we developed the model for the MR as a function of the state of stresses. We looked into first the bearing failure analysis. We calculated the Q average from both. They're very, very similar. However, the Q ultimate was a little bit different, but they came up both with a factor of safety 5.4 and 6.2. So overall, so far, you're okay. I wouldn't go with a factor of safety of 1, right? I would put a minimum probably like a 3 or something. So you're good. There's no instantaneous shear failure. Then, in one of the cases, we had the buried utilities. And then we went through the calculation of the buried utilities where you ended up with the stresses, multiply them by the stress adjustment factors. On top of the buried utility, you had 18 psi. If you're doing regular designs, right, typically you get on top of the subgrade 6 psi, 7, 8 psi. This is, you're talking, 6 inch below the subgrade with 18 psi, right? So we will find out that there might need to be a mitigation because we failed actually the flexural strength investigation. We passed the shear strength, the axial thrust, but not this on the sidewalls of the rigid pipelines. Localized shear failures also came up with factor of safety 2 and 1.6. For the localized, probably 1 or 1.5 is fine, because for a failure to occur, you need a mechanism, okay, to occur. And then this is what's the interesting part is basically when we look at equivalent FWD load levels, right? For the 12 tires with the dollies, came out 31,000 pounds. For the Continuous one was about 37,600 pounds. Huge. Standard truck, the equivalent is about 8,000. That's why we run around 9,000, right? FW testing. Now, if we went with an SSR of 0.7, right? You wanted to lower it more, but with the 0.7, give us 26,000, which seems still high, right? But you don't pass. So mitigation is a must in this case. You shouldn't let the super heavy load, either one of those, to travel on top of that flexible pavement. Even though you don't have instantaneous failures or whatever, but you're going to have excessive deflection. Okay? So you shouldn't let that happen. And here are the costs associated. Those costs are high. Why? Because that super heavy load should have not, we shouldn't have let it go through that pavement. But if I take a 50% remaining life, right, in both cases, actually what came out more critical, the AC permit deformation. So you're talking about $400 per lane mile. If this super heavy is going to travel about 10 miles, that's a $4,000 permit. All right? Anyway, but again, according to the procedure, you shouldn't allow that without mitigation to reduce the state of stresses. This is my last slide. Okay? So basically, just reiterating that SUPERPACK is going to handle a comprehensive mechanistic-based methodology that is tailored for agencies to be able to use it with current technology and current techniques. Okay? And with this is our beautiful campus. It's familiar, but it changed. We have a new building. This is a new fitness building that you haven't seen it yet. Next time you go, you'll visit it. But they call Reno the biggest little city in the world. I really didn't know what that means until I moved and I experienced that. It is truly the biggest little city because it is small enough, but big enough. It has everything. Everything from the industries, the outdoor activities, any chain, you can find it in Reno, right? And not to forget the beautiful Lake Tahoe, summertime or wintertime. If you're a skier and you like to ski, right, you get a discounted student pass, the big time. All right, with this, actually, I conclude my presentation.
Thank you for the very interesting talk. I know we're a little over time here, but at the same time, I know there will be some questions.
We can allow several questions, and then Elie can be outside for further discussion.
Yeah, I'll be here.
Everyone wants to continue. Yeah.
Any questions?
Since you are modeling the everything of accepted surface course as linear elastic, the concept of superposition worked pretty well in that situation. We've done that with looking at 777 landing gears, and it works out pretty
Actually,
well.
we're using superposition internally to come up with the representative MR value. Instead of running it multiple times and do the iterations, we're using the superposition concept very well.
Is that how you're finding the nucleus too?
Yes. Yes.
So usually then your critical pavement response location happens to be inside, in the middle, around all the other wheels?
Yes, there are multiple critical locations, but what we are, because most of the analysis deal with the subgrade, if you notice, so we focus on the subgrade level to come up with the nucleus. Yes.
Okay, go ahead.
I had some question about the C and feedback calculation for the subgrade layer. You mentioned that you will basically get the data from FWD testing first, right?
Right.
But the subgrade is a material that's really sensitive to moisture.
Right.
And so when are we doing this FWD testing?
Very good question. So now, ultimately, which will not happen, but ultimately, let's say you have a permit, you have a move, you send out your crew, you do your FW testing at the time of the move. So if it was dry, will be dry. If it was wet, will be wet. Whatever that is, you get the data back. But that will not eventually happen. What we envision as part of the implementation is that the state will have a program. And they can go out and then throughout the year do FWD testing ahead of time, right? And do the analysis separately and then have a database of your CNV.
So if you have multiple CNVs, different values over that.
You will have multiple based on the season, exactly, yes. With the seasonal variations and all of that, yes, of course.
And we'll probably get the critical one probably. Right?
either you can do it based on the critical one time and say, this is a critical and we'll move with this and we'll do the analysis. Or if you want to be picky and say, for this season, I will use this or that, that's another option. The software really doesn't care. It's more the user decision what to use. But that's a very good question. Yes.
If it is one-time passage of that super heavy vehicle anyway, it could be just due to the season or timing.
Right. But there's also what we find out, because we analyze about 10 years of data from Nevada DOT. And then there are some routes that are very common for super heavy loads. So those you might put more effort into them and get more additional work if you want.
I have two small questions. One of them is related to this question. So first one,
Make it one question.
Huh?
Make it one question.
Make it one large question.
You catch him at the
So first, when you're looking at the software, it will check the damage and the cost associated with one pass, right?
Exactly.
But what happens when you have accumulation? Like, do you need to do the testing like every year to check it? Like, do you do it once per year? This is the first question. And the second question is with the nucleus that you talked about. How do you take into consideration that there is not full recovery before the application of the second set of ink, the remaining? Because at the end, they are very
Close.
to
Well, some are really wider even, but yeah. So the first questions, which is very good questions, in your damaged E-star. So you will need to adjust. Let's say you had a move in the month of February, right? Then you have an associated E value. Then you had a move back in August, after 5, 6 months, you had another move. Then you can adjust your damaged modulus for the asphalt layer. Okay, this is one. The other thing, if there's a change in the soil, groundwater table, the material part, then this is where you can adjust also your properties for the unbound materials. Then in the case of the spacing, right? So the way we're treating it right now, that yes, the nucleus basically, remember what I said, there's a 60-inch. So under typical loading, find out that 60-inch, beyond 60-inch, you don't see the effect of that axle on the other, right? So that's why we impose that as a minimum. Now, as a user, you can go back and say, you know what, I'm not comfortable with 60, I'm going to make it 72 to allow for recovery and all of that, right? Because maybe it's heavier. But what we've observed from the analysis and everything, typically, if you have a nucleus here, or you have a load, if you have a group of axles, and then the next one is further away, 60 inches, then you'll get, there's enough space to kind of recover. Okay? So that's the reason behind that 60 inches. But we kept it as a preference in the software in a way that we can change it. The user, if the user is knowledgeable with this, can adjust it.
Maybe
Last question.
Okay, last question.
Yeah, thank you. So my question is maybe a bit related to the concept of the nucleus. I guess for starters, when you're going to give a permit to whoever the entity that is going to do the movement, they propose or they only tell what they're going to use, right?
Yeah, they propose a configuration.
But they only propose it because maybe that's what they have or based on their experience. Like,
Or based on the legal load limits sometimes. A lot of agencies tell them, you need to have that axle load is this, entire load is this, and some have more flexibility.
because my question was if, I don't know if there has been any thought of, from the concept of the nucleus, maybe finding a nucleus configuration that is less damaging, and from then kind of work back to a configuration of...
That's also very good question. So really a follow-up to this is exactly what we're talking about here. Is we can use this to optimize the axle configurations.
You're going to find the best...
Optimize it from
and then
right,
without
from
vehicle.
from damage perspective and from cost perspective. So there will be mutual benefits for the agency and the industry. But it's not that. This is just now one way. You take it, you analyze. But that's a very good point. That's what we discussed. The follow-up to this could be, how can we now develop a follow-up is to optimize that, so allow for this.
Can that be used to evaluate the loading on the bridges?
The what?
Can that evaluate the loading on the bridges?
Not really, because the loading on the bridges, you're talking about different mechanism of failure.
Yeah, I didn't know if you had.
Yeah.
Different things in the software.
No, we haven't handled that. It wasn't part of the scope of the work. No.
All right, let's thank Dr. Hajj for a very interesting.
Thank you.
Propaganda. So instead of going all the way to Lake Tahoe, he came here to present again. So that's why I think.
But I'm
we're
happy to
thankful.
be here.
Oh, you are okay. Thank you so much.